Okay, great. So for our second talk today, we'll have Viviana Acquaviva. Viviana is professor in the physics department at the CUNY NYC College of Technology and at the CUNY Graduate Center, an adjunct senior research scientist at Columbia University and the Lamont Doherty Earth Observatory, and a visiting professor at the SISSA Institute for Data Science and at the Flatiron Institute. After many happy years as an astrophysicist, she is now working at the intersection of climate science and data science.
Thank you, Katie, for the introduction. Hi, everyone. It's nice to be back here. So I'm going to talk about a project that we started recently called Tiny Ocean, Physically Meaningful Dimensionality Reduction for pCO2 Reconstruction. And I promise I'll tell what every one of those words mean. But I want to sort of like zoom out for, well, I want to do something. Okay. I want to zoom out for a second just to put this in context. And so, this just to give you a bit of a bigger picture idea of the different things I'm working on. So I have two main research directions now that I'm, sort of solidifying this transition to climate science. One project is about assessing similarity in the output of climate models. You have heard about this, and this project is led by Gabriele. Sarah is also participating in this, and I think you'll be hearing about this on March 7, which is why I decided to focus on something a little different here. And then the other thing that has occupied a lot of time of myself recently is this follow-up proposal to the Pivot Fellowship that I had that I finally completed, and it's called From Sparse Data to Full Spatial Temporal Fields, Surface Ocean Carbon and Beyond. And this hopefully is setting the foundation for a long-term collaboration with some people here, in particular in Galen's research group, like we have Abby and Thea and Amanda, who is online, and Tian, as well as some people from my old world. So Roberto is an astrophysicist in data science at CISA, which is the place where I did my PhD in Trieste, Italy, and Alessandro and Romina, who are there. They are researchers in statistical physics who are participating with, more of the sort of techniques aspect of this. So I'm excited about that, and this is where Tiny Ocean lives. So to tell you a bit more about this, the problem that we are trying to solve. When I say surface ocean carbon, that's a lot of words. So, we usually write this as pCO2, the partial pressure of CO2 in the surface ocean. And so the issue that we have is that the observations of this variable that are available are very sparse, both in space and time. So this is actually not all the ones that we have. I believe this is from a 1-year interval, but you can see that they're limited to certain trajectories. They are there are many more of them in the northern hemisphere compared to the southern hemisphere. And if you were to be able to represent this in time, you would also see that, there is like a strong seasonality effect. And, overall, if we were to grid all the observation that we have and put them on a grid of a 1 by 1 degree and on a monthly cadence, we will find that only less than 2% of the grid cells are filled. This is something that Abby and Thea also described earlier in the year. So what we want to do is a process called reconstruction, which is turning from this sparse and biased observation to a dense field in space and time. And this is somewhat challenging, but it's also important. Why do we want to do it? And the reason for this is that this pCO2 that we talk about participates in understanding what is the contribution of the ocean to the carbon cycle. And the ocean plays an important role there with absorbing about 40% of the emission from Earth. And there's still like a lot of uncertainty in the role of the ocean. Here we have about a 15% uncertainty in the most recent evolution from like the global carbon budget. But this 15% is actually limited to when we consider the annual mean. Right? And so when we look at things like seasonality or like decadal variability, the uncertainties are higher. And this number comes from combining our estimates of the contribution of, basically like of the flux of carbon between ocean and atmospheres, which is determined two ways. One is from global ocean biochemistry models, and the other one is from the so-called CO2 products. And this is the process that we are referring to here. And so this is what we are trying to do. We are trying to reduce the uncertainties on this estimate so that we can make better plans for mitigation and adaptation to climate change. And the way we are trying to do this is improving the reconstructions, basically trying to obtain smaller uncertainty in the reconstruction process. So this is sort of like a big picture map of my proposal. We try to do different things, and the reason I'm putting it here is that I would love to talk more with any of you if there are something where you feel like, okay, I'm interested in this, I have something to say, I have a suggestion, I just want to hear more. So one part is to improve the machine learning modeling. This is a process that involves machine learning, and so we can do something on that side. One part, which is an important part, is to validate the reconstruction process. So whenever you use machine learning to go from a sparse and biased domain to a domain that is bigger and has different distribution, there are a lot of risks in whether this procedure is safe, whether you can trust it, whether the results that you obtain are reliable. And so this is something that we need to validate using Earth system models. And so this is, a big part of this effort. And then another thing that we are looking at is how can we plan future observation to be efficient and useful. And so this is an ongoing project that we have with some of the people here called data evaluation, understanding what is the value of different data points that we already have in participating in this sort of like determination of the pCO2 field. And what I'm proposing is to turn this into a constraint optimization. This should read actually problem, not model. This is me wishful thinking. I have a problem and I want a model. So I already did this in my head. So the idea is that if we can describe observation as a parameterized system, then to find optimal observation, we can actually do parameter estimation. But in general, the umbrella that is comprehensive of all of these is tiny ocean, which is the idea of finding representations that are agile, meaning small, robust, and interpretable, so we can do clustering and dimensionality reduction. So in general, I feel like this, one of the reasons why we started from this project and why I'm also passionate about it is that it can help everything else by at the very minimum, making things less computationally expensive, but also helping with efficiency and so on. So I know that you guys know this, but I like this slide. So if you have seen it very recently, for example, at AGU, please do not intervene. But I'm talking about representation. So I want to give a very practical idea of what representation is. So let's say that this is a supervised machine learning problem, which means that I have to give you a learning set where both the input and the output is known. And then I ask you to learn the rule that is behind this. And I'm giving you a learning set composed of 5 objects. There is only one feature, which means one piece of information for each object. And so for input 1, the output is 3. For input 2, the output is 3. For 3 is 5. For 4 is 4. And for 5 is 4. And then I'm going to ask you to predict the output for number 6. Actually, I'm going to ask you if you can find the rule. And I'm going to give you exactly 10 seconds. 9, 8, 7, 6. No anxiety. 5, 4, 3, 2, 1. Okay, too bad. Okay, now I'm going to give you a better representation. It's the same thing. And now I'm going to ask again if somebody can figure out what's the rule and what the prediction for 6 should be. Yes. 3, very good. And why? It's a number of letters. Excellent. That's one of the fastest that I have seen. Very congratulations. And so here you can see that, I have added no information, right? All I did is like I rewrote this data in a way that was more useful. So this is what we're looking for here. Can we get an improved representation of ocean features so that overall the process of reconstructing the pCO2 field can also be improved? So I'm talking about ocean features. I haven't told you what these features are. So I want to open up the process of reconstruction for a second to tell you that it's less uh, linear than I made it. So, like from these pictures, it look like, oh, I have these, and then magic interpolation, and then this appears. In reality, unfortunately, this is something we cannot do with data that are this sparse. So instead, we have to go through an intermediate process, which is where the machine learning enters the picture, which is we also have some features in machine learning parlance. In practice, it means input variables, so just in general information that we have about the state of the ocean. So from a physical perspective, these are things like temperature, salinity, chlorophyll, mixed layer depth, and also the CO2 amount in the atmosphere. This is basically our, the only variable that takes account of the passing of time. And then also we have some spatial temporal features that tells us what is the time of the year, right? Because there is a strong seasonality effect. And then we also have some geographic features which tells us where we are on the sphere. And so these are the physical features that we can use to aid the data where the observations are sparse. So what we can do is to build a machine learning model that learns the connections between these physical features and the pCO2. And we can do it using as a learning set the places where observations are available. Now, once we have these, we can then use the machine learning model to fill the gaps because the physical features are available densely. These are something that we can usually avail ourselves of in space and time. So really what we're trying to do here is to build a representation from those variables that improves the reconstruction process. How can we do this? Well, there are many ways, but I think, maybe the first step is to say, okay, when I say improve the representation, what am I looking for? What are the things that matter to me? So again, you can answer this in many ways according to what is important to you. Like, for example, this, you can see that powerful is not necessarily something I have put here. I've put physical, which means that I don't want to stray away from the space of physical variables. And this is just because we decided that for this project, interpretability was ranked very high in our priority list. There are a lot of encoding methods that you can use to get something that is problem-aware and very small. But then you sort of like lose track of what the variables are. So for something where, that you want to use to communicate, for example, for others to be like more universal, for us, staying in the space of physical variables was important. Problem aware. Again, there are many dimensionality reduction or representation learning methods that are general. You never look at your target, at what you're trying to do. You just look at what your variables are and you ask, how can I re-represent this? For us, this doesn't work too well. So what we're looking for here is a representation that is aware of the target that we're trying to reconstruct and is sensitive to that, which also limits, in a way, what this representation can do. If you were to solve another problem or reconstruct a different field, then you would have to pick a different representation. But for our idea of improving the skill of machine learning model that predict that field and the generalization properties, which means when I go outside of domain in my reconstruction, can I trust what I've learned? This is quite important. And finally, we want a representation that is small, possibly tiny. That's where tiny ocean comes from. And you can do dimensionality reductions in different directions, right? If you have a data set that has a bunch of rows, these are your objects, and then a bunch of columns that typically are your features. We often talk about dimensionality reduction in the feature dimensions, like, okay, can I represent my data with fewer variables? And that's nice, and one of the things that we want to do. But we can also do dimensionality reduction along the dimension of data points. And this is sometimes, you can think about it as clustering data that are very close to each other. And so we want to explore both. One reason is it makes problems more tractable from a computational perspective. Another reason, which is related to the feature dimension, is that if you can get to a final dimensionality in feature space or 4 or 5, now you start to be able to visualize things. Like 3-dimensional you can plot to, a color you can add. Perhaps, you can figure out a shape or something for your markers, which means that, 4 is really the magical number, but even with 5, you can start to work. And now you can physically interpret what your data are. You're not anymore in a space that has like 10, 12, 15 dimensions, which is the starting dimensionality of our physical space. You can actually, look for trends, and this is really helpful when you want to, interpret the relationships that you find. I might do. Okay, so there are two sort of ingredients of the tool that we have used. The first one is when we talk about representation. So we are looking for, I think I wrote it here. I'm not very good at keeping notation consistent. So, when I talk about representation, you will see me talking about a metric or a distance or a combination of feature variables. This is what it means. Just bear with me with improper language. So one of the things that we ask is, how do we evaluate the information content the different representations or metric have? And so this is a very simple idea. Let's say that, I'm just comparing two variables or metrics. This is, basically a one-dimensional representation. That's why there is only one variable. It could be bigger, but then again, we'll be able to plot it. And so we want to compare the content of information in X and Y. We start from Y, and so something you can note is that if points are close to each other along the Y-axis, you can see that they're also fairly close to each other on the X-axis. Just an observation. However, if points are close to each other along the X-axis, as you can see, this doesn't mean that they are close to each other on the Y-axis. So in terms of information content of these two metrics, the way we can interpret this is that Y is more informative than X, because vicinity in Y is predictive of vicinity in X, but the vice versa is not true. Okay, so this is one ingredient. This is one way we can think about how informative different metrics are compared to each other. This gives us a way of comparing them. The other ingredient for this is interpreting distances as neighbor ranks. And so the idea here is that if you have different distances or metrics, you can calculate what is the closest neighbor according to the metric for each point that you have. And this may vary. So this is, you can see here we have point I and point J. According to space A, that weighs some directions differently. J is the first neighbor of I, but according to another metric, J may be the third neighbor. So of course, their neighbor rank will depend on what distance metric you use. But what is nice about this is that this is a type of distance that is insensitive to the physical scale of your variables. And so in a problem like ours, where we are mixing physical features, we're mixing things like latitude and longitude, we're mixing things like time of the year, this is really nice to have. It's a very nice property. So putting them together, we can define something called information imbalance. And this is basically tells you what is the information loss when you move from one metric space to another. And the idea is that you calculate the ranks, which means like, for each point, what is the neighbor rank of all the other points in the data set. And then you calculate the average of the ranks according to distance B of all the first neighbors according to distance A. And this you call the information imbalance between A and B. So let's think about this. Let's say that, we're going from space A to space B. Now I look at the neighbor ranks of all the points according to metric B. They were first neighbors according to metric A. So if these two metrics are aligned, then the first neighbor according to distance B, according to distance A, would also be the first, or maybe second or third, but a very small number according to distance B. Instead, if we are in a situation where distance B is not contained at all in distance A, which means that you lose a lot of information when you move from one to the other, you will find that the neighbors are distributed maybe uniformly. And so you end up with an average which is not close to zero. It's bounded by one, but it's certainly not close to zero. And so you can build this representation. This tells you the information loss going from A to B. This tells you the information loss going from B to A. Of course, they're not symmetric. Like in the example that we had before, one metric was more informative than the other, which means that we're not going to be at this corner or this corner. We're going to be here or here. Like one of them is contained in the other. But this gives you a way of representing the information loss. And now we can use this to generate our improved representation. How do we do it? Well, we have our target metric. This is the information we want to have, which is the proximity in pCO2 space. So we can calculate that neighbor rank. Then for any candidate metric that we can build, which means let's take our feature space and just build all the possible combination of distances. We can do it without weights, or we can do it with weights, which makes it more general. Now we can calculate the information imbalances between our target metric and any possible candidate that you can build. And the goal is to find something with the smallest information imbalance versus your target, which is the pCO2. You don't need to find something equivalent. You just need to find something that contains the information about pCO2, which means that if this is the asymmetry going from your physical variable to pCO2, you want to stay in the bottom part of this plot. So this is what we did. And the nice thing, sorry, that I forgot to mention is that you can do this as a function of the number of dimensions so that you can find your optimal representation for every dimensionality that you want to explore. So finally, I'm showing this is an actual scientific result after all this talk. So this is what we did. We started with a subspaces of 11 features, which were the physical variables that I presented. And then usually 3 are used to have latent load on the sphere. We need an extra one to have periodic condition. Excuse me. And 2 are used for time of the year. Again, to impose periodic conditions, you add another one. And so what we found is that this is like the asymmetry of information. You never go to 0. Okay, I think like the lowest that we had was around 0.4. However, you can also see that as you go from like 2 features to 11, you have a point of maximum return. And for n equal 5, I mean, arguably this is n equals 6. But 6 was too much for me, so I chose 5. I feel like, 5 is probably where the elbow of these curves is. And these are where the points go. And so what this is telling me is that if I only use 2 variables, my information imbalance is very high. With 3 variables, it goes a little further down. With 4 variables, a little further down. And then here, this is where it starts to converge. And so with 5 variables, which is this point here, I have a reasonably small information imbalance. And with 6, I can do a tiny little bit better. What can we do with this improved representation? Well, we can do different things. As we mentioned, we want to use it for visualization, for interpreting data points. We can also use this new distance metric for clustering, right? Clustering will be more effective because most of the clustering methods are based on distance. If you have a distance and knows what points you want to put together, this is good. However, one of the things that we can also do is to go back to our machine learning modeling, perhaps the simplest thing, and see, now that I have a better distance, can very simple methods, for example, KNN, k-nearest neighbor, become more powerful? And this is what I want to show. I have, 2 minutes. So again, I'm trying to build the model so that from the physical features, I learn the pCO2. The state of the art for doing this on data is an algorithm called XGBoost. You can also use a neural network, but this is essentially tabular data, so you don't use two. They are essentially the same. XGBoost is a model, very nice model. It's built on decision trees. They're sort of like the basic estimator. So you build decision trees that ask binary questions about your features. make a predictions, and then you refine them. Basically, at each stage, instead of predicting your target variable, you try to predict the residuals of the previous stage model. So you make a correction. And this works because in practice, the residuals are the derivative of the mean square error loss, which means that in practice, you're taking gradient descent step along the loss function. That's a reason why it works. And we're going to compare it to a very simple method called k-nearest neighbor, which you don't even need to do training. If you have to make a prediction for a new object, for example, this one, you just say, okay, I'm going to look at the k closest examples in the training set. And then for a classification problem, you just output the average of the class. And for a regression problem, you output the average of the target property for those points. So this is an example in which, for example, for this point, if I chosen k equal 5, I just look for 5 examples in my training set. And then I said, okay, for this, let's say that I want to output the pCO2 for this point. It's just going to be the average of those. You can weigh according to distance, but it doesn't matter. So we start with 11 features, and we build the model using KNN and XGBoost. XGBoost is here, and here is KNN. And you can see that the 11 features, they perform quite similarly. I mean, this is just a visual thing. I'm plotting median absolute error at each point. And then we reduce the dimensionality. In XGB, the way you reduce dimensionality is that you do a feature ranking, and you start eliminating less important features. In KNN, you're using this best distance that I told you about to do your dimensionality reduction. You can see that with 5 features, this is essentially stable, but this is quite a bit worse, which tells you that, yes, at the beginning, they're equivalent, but to go to a smaller dimensionality, this distance is really powerful. And you can look at other measures of model skills. For example, this is like the median absolute error, saying in one case is stable, and then it goes up. This is the R2 score, which is a measure of model skills, so higher is better, and has the same behavior. So I'll conclude saying we are excited about this information imbalance. Well, I am very excited about it as a way of building optimal representation for fixed dimensionalities. You can use it for many things. And another thing that I'm particularly excited about this is that I know that there is a potential for further improvement because using 5-dimension space and time for something that physically has only 3, we know it's something that we could do better on. And so if we were to get to d equal 4 in particular, this would be very exciting for our data evaluation process. But in general, it's a very general pipeline. And so if you have similar properties, similar problems where you have a physical problem, you want to go to a reduced dimensionality space, I'd love to talk to you about it. Thank you.
Thank you so much, Viviana, for a great talk. Any questions from anybody in the room?
Hi, very nice talk.
Thank you.
I have a question on the slide that you had with nice 2D plot that shows the informativeness of your, now go back. This one. So if you pick a different set of 2, for example, if you pick right at the beginning, XCO2 and for example, SST, would you get like a larger drop right at the beginning? Like, is it sensitive to the pair that you pick at the beginning?
Yeah, actually, this is not picked at the beginning. It goes from 11 to 2.
Okay.
But for every actually, no, I take it back. It's done independently in every dimension. So it's not a stage-wise process. I say, okay, so I only fix the number of dimensions, and then it does a search for the weights. And we do it with L1 regularization, so it encourages sparsity. So in a way, each dimension is independent, but basically, yes, it's not a specific order.
Okay.
But I think for a fixed dimensionality, the pair is always the same.
Okay. Thank you.
Thanks for the presentation. Regarding information imbalance, does it compare to information theory measures that are well-grounded theoretically, but hard to compute in practice, such as the mutual information, for example?
So I'm not an expert on this. I read the papers, but I think I should really reread the papers to tell you. But from what I understand, yes, my understanding is that this is sort of like a how is it called? Like a heuristic estimator of the actual mutual information
So
content.
it's expected to approximate or converge
Yes.
to, in some
Yes.
limits, to the
Yeah.
mutual information?
I think so. At least this
Interesting.
is my understanding of it.
Okay, thanks.
You're right.
Okay. Thank you so much, Viviana, for a great talk. And we hope everybody will stay and enjoy light lunch in the kitchen.